Michael reactions are a way of putting a weak nucleophile on the beta carbon of an aldehyde or a ketone. So you always start with a weak nucleophile, and you'll end up with that weak nucleophile on the beta carbon of an aldehyde or ketone. Now what you need to do that, always, will be an alpha-beta unsaturated aldehyde or ketone. So remember, the carbonyl carbon is the one double bonded to the oxygen. Next to that you have the alpha carbon, after that the beta carbon. If you have a pi bond between the alpha and beta carbons, that is alpha-beta unsaturated. We've seen these before. These were the products of aldol condensations. So if you go back to the videos on aldol condensations, you'll see those products, alpha-beta unsaturated aldehydes or ketones, are now coming back, and they're going to become reagents. So this is sort of what we can do even after that other story ended. We can take those characters and build this new story with them. We can do these Michael reactions. Now, to see why these things are happening, because at first, if you look at this, if you think about this, a nucleophile usually has a slightly negative charge. Nucleophiles either have a full negative charge, a partial negative charge, a lone pair, or a pi bond. Those are the only ways nucleophiles are ever represented. They're associated with negative charge. So why would a negative charge attack this beta position, as we see it doing here? That means this beta position would have to be an electrophile. And if you look at this molecule, it does not look like that as an electrophile. On the contrary, what you'd see there is a pi bond, which is a nucleophile. So let's think about this alpha-beta unsaturation for a second, and we'll see why that beta position truly is an electrophile. Okay, well, when you see this, we actually have a resonance pattern here. We have a pi bond between two atoms of differing electronegativity. That's one of the 5 resonance patterns that you would have learned in Organic Chemistry 1. And I have videos to practice those if you'd like. If you'd like me to, I can send you a link to those. So because we have resonance here, we're going to draw brackets to warn the world that the true structure is none of these structures inside these brackets, but it will only and always be the average of them. So when you have a pi bond between two atoms of different electronegativity, to get the other resonance structure, you move the electrons in the pi bond onto the more electronegative atom. So we draw a special resonance arrow, 1 line, 2 heads, that tells people take the average of these molecules on either side. And that other resonance structure, this had 2 lone pairs originally, this will now have 3, and a full negative charge on this oxygen, and a full positive charge on this carbon, which is now missing electron density. Okay, well, that's one resonance structure. But in this second resonance structure, we have a new resonance pattern. We have an allylic positive charge, a positive charge that's 1 atom away from an atom in a double bond. You'll remember this positive charge is an empty p orbital. You have parallel p orbitals in that pi bond, so the electron density can spread out over all of those, and that gives rise to this resonance, which resonance is just a way of accommodating our sort of stick figure Neanderthal-like drawings or rather very primitive drawings to what's actually happening, which is the electron spreading out. So to draw that next resonance structure, we move those pi bonds toward the allylic positive charge, and we end up getting this molecule here. The pi bond moves over, but now the beta carbon is missing the electron density that it had from the pi bond, so it has a full positive charge in that resonance structure. Now the true structure never looks like any of these. The true structure always only looks like the average. So let's sort of do a mock-up, do a rough draft of what the true structure might look like, or, approximately. At least try to visualize different features that are happening here. In the true structure, these are somewhere in between single and double bonds, all of them. The oxygen is here. And then, right, because if you have a double bond, but then single bond, if you average all those, it's something in between a double and single. You could do that for all the bonds here. The oxygen has a slight negative charge. The carbon here has a slight positive charge. You can see one of the resonance structures has full positive, but 0 in the other, so add those together and average them. You end up getting a slight positive. And the beta carbon also has a slight positive charge. It's 0 in the first two resonance structures, but full positive in the third one. So altogether, that has a slight positive charge. So that's maybe more, even though that's not a technically correct chemical Lewis structure, that is sort of represents what the molecule more truly looks like. And what you see here is that on the beta carbon, so this is the alpha, this was the beta carbon, we have a slight positive charge. And that's the reason why a nucleophile would attack that beta carbon, to attach there. Now, it does have to be a weak nucleophile. That's an important point. An experimental fact is that if we take this molecule, and here I will just take this more conventional drawing, if we take this molecule and you treat it with a strong nucleophile, it attacks the carbonyl. So, strong nucleophiles attack the carbonyl carbon, and the weak nucleophiles would attack the beta carbon. So there are a couple types of weak nucleophiles that I want to show you. The most important one are Gilman reagents. It's a carbon-to-carbon bond-forming reaction. So let's contrast that with the more familiar Grignard reagents. If you treated this molecule with a Grignard reagent, so an alkyl group bonded to magnesium bromide, and you follow that up with the water wash, you would end up with the Grignard, the alkyl group, the nucleophile, the carbon, the R group, attaching to the carbonyl carbon. It would attack, it's a strong nucleophile, so it would attack the carbonyl carbon. Contrast that with what happens if you add a Gilman reagent. If you add a Gilman reagent, and remember, those are those copper-lithium reagents, dialkyl. So you have two alkyl chains attaching to copper and lithium, and then you follow that up with water. This is still a carbon nucleophile, but it's a weak carbon nucleophile. You only add one carbon chain. Oops, this should still have that pi bond there. What ends up happening here is the carbonyl carbon is not attacked. Rather, the nucleophile, the R group, attaches to the beta carbon. This is an experimental observation. So if we say strong nucleophiles, like this Grignard would attack here, and weak nucleophiles, like a Gilman reagent, would attack the beta carbon. So it's a competition between the alpha and the beta carbon. So we want a beta carbon, and we want in these Michael additions, we're adding something onto the beta carbon. So if we're trying to add a carbon there, make a new carbon-to-carbon bond, if you want to add a carbon to the beta carbon, you use the Gilman reagent. There's another type of reagent that's really useful, especially because it'll help you understand the Stork-enamine synthesis, which is the reaction after this. And that's if we've seen how these alpha carbons can be acidic. The hydrogen can be ripped off, and you can create nucleophiles out of them. Now, if you only have one carbonyl, remember this is in a p orbital, that's parallel with the p orbitals in that pi bond, so that's resonance stabilized. But this is not very, very resonance stabilized, it's just a little resonance stabilized, and so this is actually a strong nucleophile. This would be like a Grignard reagent, and it would attack the carbonyl of this alpha-beta unsaturated aldehyde. But what you can do to stabilize it even more is to have a second carbonyl. And now those electrons in the lone pair are in a p orbital that's parallel to the p orbitals in this pi bond and in that pi bond. They're spread out over 5 atoms, so they're much more stabilized, and now it's a weak nucleophile, and it would attack the beta carbon of an alpha-beta unsaturated aldehyde or ketone. Okay, so so far what we have determined is that first, the beta carbon of an alpha beta unsaturated aldehyde or ketone, that beta carbon is electrophilic. That's the first thing, because of resonance. The beta carbon is slightly positive. And the second thing we've determined is that whatever we want to attack there, we want it to be a weak nucleophile. A weak carbon nucleophile are Gilman reagents, and another weak nucleophile are these molecules that have an alpha carbon between two carbonyls, alpha to two carbonyls. Okay, so those are important concepts. And now that we have those concepts down, I want to take just a second to sort of draw the mechanism out for this, which is a little complicated. But notice the overall effect is you add the weak nucleophile onto the beta position and you just erase the pi bond. That's the overall effect. But the mechanism is a little bit more involved, so I want to draw that out just in case you're interested. So let's say we have we have this alpha beta unsaturated ketone here, and we're going to have a weak nucleophile. Now, just so it's not quite so cluttered, I'm going to erase the word weak here, but it's a weak nucleophile. Okay, well, if it's a weak nucleophile, it will attack the beta carbon, and these electrons in this pi bond will get pushed over. They'll go toward the slightly positive charge in the carbonyl and kick these pi electrons up onto the electronegative oxygen. So what you get after that first nucleophilic attack is an enolate. Oops. Actually, let me take this so you can see the arrows moving. So this pi bond will break. That will become a lone pair on this oxygen, which now will have a negative charge. This pi bond will move over, and your nucleophile will attach to the beta carbon. And so notice we have an enolate. We have the double bond, an alkene, and almost an alcohol attached to it. That would be an enol, but the alcohol lost its H, so it's an enolate. So that then can do a proton transfer from hydronium, and this is why the hydronium is in the recipe here as the second step. So this oxygen has a full positive charge. The negative charge to oxygen can steal a slightly positive hydrogen there, and after that proton transfer you have not the enolate, but the enol. So we have an enol. And then you'll remember, and this isn't the place to draw this mechanism, I have other videos from this from Organic Chemistry 1, and also from the beginning of this chapter, but you'll remember that anytime you have that enol, you get tautomerization. Most of the enol, you always have the enol existing in equilibrium with an aldehyde or a ketone, but most of it will be the aldehyde or ketone, and so here, you just move that hydrogen around, and that tautomerizes. That means you move the position of just one hydrogen and any electrons to make that happen. You do that mechanism that we explored in the first 4 videos of this chapter, and that you would have been exposed to in Organic Chemistry 1, that tautomerization, and you turn the enol into the aldehyde. And so that's how you get your final product. So it's really a nucleophilic attack with some complicated electron shifting, and then a proton transfer, and then a tautomerization. But what it ultimately looks like at the end is that you added the nucleophile onto the beta carbon, if it's a weak nucleophile, and then you just erase the pi bond there. But now, hopefully it makes sense what we do, why we use that hydronium. It's to create the enol out of the original enolate so that it can tautomerize. So hopefully this video helps you a little bit with understanding the concepts behind the Michael reaction, and also the mechanism for how it works.